All right, this is video lecture 6.5, and we're really just continuing here with uh, going through these 7 most common threats to internal validity in scientific studies. So the next one we're going to talk about is statistical regression. I'm sure you've heard this, regression to the mean. Right? So all this is the tendency of extreme scores or extreme results to move closer to the mean. And the reason this happens is that whatever your extreme result was based on extraneous factors that didn't really have anything to do with your experiment. So a classic example of this is, which I think is talked about in Statistics Without Tears. If you give 100 students a quiz, and then you choose the 10 students who got the 10 worst scores, and you give them special tutoring, if you do that and then you find out that those 10 students improved their scores on later quizzes, you have to worry that regression to the mean might have been part of that result, right? Regression to the mean here might threaten your ability as a scientist to validly attribute any improved later test scores to your tutoring, because at least some of the students who got those low scores the first time around might have done badly for some other reason aside from inherently poor study habits or intelligence, like maybe a couple of those students were sick or upset the day they took the test. Maybe they studied the wrong material and showed up for the test just not having studied the right material. So those chance factors, right, those are not statistically likely to be repeated on future testing occasions. So those students' scores are probably going to go up no matter what you do. So with this kind of research design, if you're choosing subjects based on their extreme scores, then at least some of the subjects included in your study group won't really belong in that group and will tend to score closer to the average score on subsequent tests, completely independently of whatever you do as your independent variable. And of course, the same would apply if you chose the 10 highest scoring students and gave them special enrichment classes. There's going to be a tendency for at least a few of those students to score lower on future tests because maybe they were really just average students who guessed well or had a particularly good day or studied unusually hard, but they'll be unlikely to score as high on later tests. And that's where the phrase regression to the mean comes from. I haven't played golf in a number of years now with all my back issues, but I always think about when I did play golf, I would have a couple of holes where I would play really well. And I actually tried really hard not to imagine this was me getting better at golf, but usually it was, you know, an extremely good couple of holes, and I would very soon regress to the mean, like I'm about to do in this photo where I'm about to hit the ball into the water. Okay, so the next threat is the selection threat. So this refers to the possibility that the groups that were studied, the groups that were compared by a scientist, which are supposed to be as equivalent as possible before the independent variable gets applied, right? The variable of a treatment or some intervention. But in a selection threat, what you're worried about is that maybe the two experimental groups or two or more experimental groups are actually unequal in some relevant characteristic before the treatment intervention happens. So this is a particular concern anytime subjects can't be randomly assigned or just aren't randomly assigned to one group or another. And the book uses the prison program example, right? Studying the effects on recidivism. So if you allow prisoners to self-select, to be in your, say, your educational program, you might end up with the more highly motivated prisoners in the program group, and they would frankly be less likely to commit later crime when released than the control group, no matter what. So that's going to skew your recidivism data. And I have just some other examples on the slide here. If you're testing an experimental medical treatment for a particular illness, maybe you choose relatively healthier people with that illness to get the experimental treatment because you're worried the treatment might have some pretty intense side effects, and you think those healthier, stronger people could withstand that better. But that, of course, leaves your control group having the, more of the less healthy people that have that illness. So it's going to be close to impossible to distinguish the effects of your treatment from the effects of the initial health differences in the groups. So that's clearly a selection threat. Another one, of course, you see the posters in the basement of the 198 building announcing that students who took Barbary were more likely to pass the bar than students who didn't. This is clearly subject to selection bias, right? Maybe the better students were overrepresented among the group who chose to take a Barbary course. And it was in fact that, rather than the course itself, that may have produced a higher pass rate. You could have the next one, a study comparing weight loss programs between people who chose to lose weight eating Subway sub sandwiches and people who joined Weight Watchers. Maybe people doing the Subway diet might do better for some other reason. I used to say maybe they're more motivated to do well, hoping they could be the next Subway commercial spokesperson like Jared. But if you're familiar with Jared, he actually turned out to be a child pornographer. So probably not somebody that people are going to want to emulate. But of course, with Jared out of the way, if you do well on the Subway diet, then I guess it's wide open for you to become the next spokesperson. The next one's kind of interesting. If you had a study on aggressiveness comparing students from one college dorm to those from another college dorm, and you take one dorm students and put them through a conflict resolution course, for example, and then measure their aggressiveness in some way. If you started out with one dorm with all scholarship football athletes and the other full of music majors and artists, now you might have a selection bias because there could be big differences in their aggression levels before your course. The next one, studying cancer rates between two communities, one of which has been exposed to higher levels of benzene in their air. Now, if one community that you're studying is primarily rural and the other one urban, now you might be in trouble because the subjects could certainly differ both in their personal characteristics and in their environmental effects, aside from that benzene exposure, like whatever background pollution might be there. So another selection threat. And then the last one I have on the page, if we wanted to study satisfaction with the practice of corporate law. Satisfaction with the practice of corporate law, you're going to interview or survey people. If you interview or survey only partners in law firms, why is that possibly a selection threat? Well, the one I think of is that everyone who wasn't satisfied with corporate law left that practice before getting to be a partner. So, and certainly therefore before being in your studies. So that's going to be skewed, of course, to show satisfaction with the practice of corporate law. All right, the next threat, mortality threat. So despite my illustration here, this is not about your study subjects dying. Instead, it has to do with study subjects dropping out of your study for a non-random reason. So in any study that's going to go on for some length of time, you're going to expect to lose some of your subjects. But if your study groups are well randomized when they're assigned to the groups, and then random subjects drop out for random reasons, you as a researcher can still safely assume that the subjects remaining in your various study groups are still random and representative. But so let's talk about this. Let's say you have a weight loss study. You're looking at a new weight loss drug. You have 50 subjects in the treatment group getting the drug rather than a placebo. And let's say 20 of your subjects dropped out during the course of the study. Well, now here, you as the scientist would have to look really carefully at that. Let's imagine the remaining 30 subjects in your treatment group lost an average of 10 pounds without any side effects from the treatment, whereas your control group getting the placebo drug only lost 2 pounds. Now that would look pretty good for your new drug, but you'd still have to be cautious. You'd have to look carefully at those 20 people that dropped out. Maybe they might have left the study because they gained 20 pounds. Maybe they had a bad skin reaction to the drug or something. So hopefully you'd have been keeping ongoing data on these folks, and you'd have some idea what was going on with them during the time they were in the study. Because if they didn't, in fact, drop out for random reasons, that's going to be something that you have to document. Okay, so aside from the big seven deadly sin threats we can talk about, there are a few others. And one of those might be that should be considered is that some of those big seven threats can actually be working in concert, right, to amp up the confounding effects on your data. So a really common one of those is the selection maturation interaction, selection maturation. So in this situation, people that you choose to be in your different conditions of a study might differ in that subjects in one group are maturing at a different rate or to a greater or lesser degree than those of the other group. So for example, in a medical study, patients who are younger or older or more or less healthy might heal at different rates, right? Or you might have a social science study where you're looking at learning outcomes of certain teaching techniques. Well, students of certain ages might learn at different rates, or a more broad example that we can talk about is if you're studying the effects of a certain kind of economic assistance to developing countries, right? Differences between countries that you're studying and their level of economic development prior to receiving whatever assistance you're studying, not to mention whatever unique social challenges might be there in a particular country, right? Those are almost certainly going to affect your outcomes in your study. Next, we can never ever forget about just the action of chance, right? Even if a researcher does everything right and randomizes really well and tries to make two groups as identical in every way, aside from the independent variable, the results might still be confounded just by chance differences between the groups. And of course, you can never fully protect any study from the operation of chance, right? But that's one of the reasons scientists and statisticians came up with the concept of statistical significance. Statistical significance is just a measure of how confident you are that chance is not causing the effect you've seen in your study, sort of acknowledging the potential for chance to be affecting it, but trying to quantify your confidence level in that your whatever differences you're seeing are a result of your independent variable rather than chance. Next, we have the potential confounding effect of variable distortion. Variable distortion. So that's just a problem with the independent or dependent variables themselves. Like, for example, faulty operational definitions, right? If a variable isn't adequately and meaningfully operationally defined, then the study data aren't going to really answer the question the research is claiming to be answering. Another potential problem might be the failure of the chosen research protocol to actually administer the stated experimental manipulation, right? So let's talk about, again, our prisoner program example, right? If the prison program isn't actually carried out as it was designed by the scientists, right? Let's say the prison facility doesn't carry it out correctly or doesn't allow it to be properly carried out, then of course the results are going to be meaningless. Or another example, if you're trying to do an epidemiological study on people who were exposed to a toxic substance, right, as compared to people who weren't, that often relies on self-reporting about exposure, right? And in that situation, your supposedly exposed group might not really have been exposed at all, or might have been just minimally exposed. Another example, a psychological type study where you're presenting certain information to subjects and gauging their responses. Maybe, and this is sometimes done in sort of a sneaky way, like you try to put certain things in a video or a written excerpt you're asking your study subjects to read about or watch, and it's supposed to be kind of subtle. But if your study subjects, if it's too subtle and your study subjects don't perceive what you were trying to make them perceive, then your results are, of course, completely meaningless. So for example, let's say you were doing a jury study and you wanted to see if your mock jurors react in a different way to a wealthy corporate defendant as opposed to a regular middle class defendant. If your mock jurors don't actually perceive your wealthy corporate defendant as being wealthy because you were too subtle about it, then you're not really testing anything. So in a case like that, researchers will often devise really creative ways to test whether the subjects actually did perceive the things they were trying to induce them to perceive. And that's called a manipulation check. So for example, in that jury study, you might ask some questions designed to get across whether your mock jurors understood that your defendant was wealthy versus middle class or something like that. And the last important validity threat that I want to talk about is floor and ceiling effects. So if one of your experimental manipulations is just so strong or possibly so weak that there's really not a possibility of differences between your groups, then you can't test the effect of some experimental treatment. And this one, my favorite example here, not surprisingly to most of my students, is my argument about why law students should want more difficult exams with significant time pressure. At least more difficult but fairly straightforward exams, right? Not those exams where the egomaniacal professor makes it a goal to write questions that, you know, in and of themselves are incomprehensible just to make himself or herself feel intellectually superior. So not those. But more straightforward but long and time-pressured exams. The point is, if an exam is too easy, you're going to get that ceiling effect, right? Everybody's going to do really well. It's then really hard to distinguish an A from an A minus or a B or B plus or even B minus, right? And the same applies, of course, with a really arcane exam or esoteric, right? If you have one of those exams where nobody has any idea what the professor is even asking, then those scores might be so low, there's going to be a floor effect with a similar result. So here again is our frustrated law student. So here he's getting his grade in a class where he walked out of the exam thinking, wow, that was really easy. I love this professor, and all of his friends in the class, you know, thought, yeah, like this professor is awesome. They were all feeling a lot of love for the professor, this nice and easy exam with no time pressure. But now our friend is looking up his grade, and lo and behold, he got a random B minus. Well, why can that happen? You know, again, because the exam was too easy. And you end up with a glom of students all scoring about the same because of that ceiling effect. Mock jury studies, again, a great example of this potential threat. So for example, if you have a case fact scenario that is just too skewed in favor of one verdict or another, then both of your mock jury groups are going to tend to vote the same way. So just like, you know, in the cases they choose for our mock trial classes or mock trial competitions, you do want to choose case scenarios that in jury research that are ambiguous enough to allow for different plausible verdicts, right? So that any differences you see in your different mock jury groups can be attributed to whatever experimental manipulation you're doing. So, for example, if you were just testing 6-member juries versus 12. All right, so those are just the most common threats to internal validity. Remember, they're not all fatal flaws, and no one single study has to control for all of them, right? If a study can definitively eliminate even one plausible hypothesis that could account for the results, then despite some internal validity problems, that study might be quite valuable as a piece of the overall scientific puzzle. And then, we'd imagine that future research can try to eliminate the other plausible hypotheses, right? The important thing for scientists to do is to be explicit about which threats to validity you're eliminating, and certainly whatever internal validity threats might have been present when you write up your research for publication. You should always include a discussion of all the potential threats. You should talk about what controls you put in place to minimize them, and have a discussion, an honest discussion about how much the data could have been compromised by any of those. So that's the kind of thing a quality scientific journal is going to always look for when deciding whether to publish something. And in fact, in the peer review process, if somebody hasn't done that, they're going to be raked over the coals by their peer reviewers. Okay, so now we're going to switch from talking about internal validity to external validity. So remember, external validity just refers to the generalizability of research to other people, to other settings, or other times. So the question is whether you can extrapolate from the subjects in your study, given your study's design, to other contexts not specifically studied. So example on the slide here, does research that indicates high rates of tumors in mice that are exposed to benzene, can that generalize to humans exposed to benzene, and at what doses, for example? Or looking at external validity in the social science arena, a lot of psychological research uses simulation techniques, right? Like our jury studies with mostly undergraduates acting as jurors. And the question is, can studies that just present a written description of a trial to college sophomores be generalized to a real case with real jurors, right? Certainly it's a different situation. The stakes are different. The people are different. So, of course, the results might generalize, but that's always going to be an issue with simulation research. So in the assignment, I assigned you some additional videos on the Stanford prison experiment, which of course you'd never get Institutional Review Board approval for nowadays. This was done in 1971, so I hope you enjoy those materials. If you're interested, there's a full movie that they made that I watched. It was pretty. It's a pretty disturbing movie, but they basically just replicated exactly what happened in the study for the film. These last couple of slides basically go along with the paragraphs that I put in your science, in your assignment. So I talked about the fact that simulation research is often used for all of these reasons, right? It's easy to randomly assign subjects, facilitates somebody else trying to replicate your study, gives you access to processes that you otherwise wouldn't have available, right? I mean, you cannot study jury deliberation inside the jury room. Jury rooms are essentially black boxes. And then, of course, the last reason scientists use simulation studies is that they're relatively inexpensive. And this sort of goes along with the paragraphs in the assignment too. If you're just testing theory, then maybe realism is less important than whatever internal validity you have. But if you want to predict, right, if you want to predict behavior, then external validity becomes more important. So certainly it's true that sometimes there are trade-offs between internal and external validity. Okay, this is the end of video lecture 6.5.